So sometimes we want to assume that the intercept is 0 in linear regression. So that is this model. So originally we have the beta naught intercept to ensure that the error has mean 0 and also the effect when all x's are 0. And this is non-standard because often statisticians, they don't care whether or not the regression line goes through origin, even if logically it should go through origin. For example, the x-axis, maybe x is the maybe the size of the right lung volume, and the y is the left lung volume, or something like that. Then one is 0. It's naturally the others are 0 because the both scale is 0. But sometimes we don't care. So even if you include the intercept, probably no one complain it. So that is one reason that this model is not that popular. And also the theory is pretty different from the usual linear model, as error cannot achieve the mean 0. Okay, example. So abalone, length, and weight. So think about the relationship between the abalone length and weight. Since length is one-dimensional and weight is three-dimensional, the quantities, we just make the cube of length. Then x-axis, the length cube, and the y-axis weight. Then this is almost linear relationship. And if the abalone size is 0, then both should be 0. So logically, it should go through origin, and also that this data looks it goes through origin if we fit a straight line. So we try the two models. So one is with a line the through origin without intercept, and the other is usual a line may not go through origin. A line through origin, the code is here. So weight on -1 plus length 3. So this is the format, the grammar in R. So -1 exclude intercept. And we can see the coefficient of length 3 estimate is 5.02 with standard deviation 0.01. So it's very highly significant. We would explain this later, and adjusted R squared is 0.9825. And the sample code line may not go through origin. So this is usual linear regression model, and we have intercept and length. And actually, even though the line looks to go through origin, still the intercept is slightly significant. So t-value -2.2, p-value 0.02. And of course, the length is still the very important variable. And the multiple R squared, adjusted R squared, 0.9325. And adjusted R squared looks smaller for LM1, actually smaller, but actually the AIC is better for this second model because AIC is smaller, smaller is better. Why this happens? Yeah, so one reason is that adjusted R square isn't necessarily consistent with AIC, but also adjusted R square for regression without the origin. So that is pretty different in terms of the definition of adjusted R square. And actually, if regression, we require the regression goes through origin, then SS total is summation of yi square. So SS total is usually the variation in y, so summation of yi minus y bar. But this regression, that we don't have any intercept, so the null model isn't really y is equal to beta naught. So we don't have a y bar term. So adjusted R square and R square is comparable because SS total is the same for all models. But here, the SS total is different. So this has entirely different meaning. So we cannot really compare these two adjusted R squares. And in this case, actually the AIC is much better for the later model, LM1. So it's reasonable to support LM1.